Suppose we have a classic Hess's law problem. Hess's law problems tend to be very similar. In the Hess's law problem, you are going to determine the amount of energy a chemical reaction will have based upon other chemical reactions that you know the amount of energy for. And a typical example might look like this, in which you have a target equation in which 2 moles of phosphorus plus 5 moles of chlorine are producing 2 moles of PCl5. And the amount of energy, or the delta H, is unknown. Question mark. You're typically given 1 or 2, or possibly, you're given either 2 or 3, sometimes 4 equations. In this case, you're going to be given one equation in which PCl5 reacts to break down into PCl3 and Cl2, and you know the amount of energy for this reaction is 87.9 kilojoules. And in the second equation, 2 moles of P plus 3 moles of chlorine, and they will react to make 2 moles of PCl3. The energy for this reaction is negative 574 kilojoules per mole as well. We like to take our target equation, the equation for which we don't know the amount of energy for, and I like to make a box around it because I'm going to spend most of my time focusing on that. So in my target equation that I have boxed, I need 2 moles of phosphorus to react with 5 moles of chlorine to make 2 moles of PCl5. And I don't know how much heat would be evolved or absorbed in that reaction. I'm going to manipulate equation 1 and equation 2 so that when I add those two up, I can equal my target equation. Well, let's start off by looking at a target equation. In the target equation, we have 2 moles of phosphorus. I'm going to go ahead and try to find 2 moles of phosphorus in either the first equation or the second equation. And I found it. In equation number 2, I have exactly 2 moles of phosphorus. That's exactly what I want, and it's on the correct side. It's on the reactant side. So I'm going to leave equation number 2 as written. In equation number 1, I have PCl5, and in equation, my target equation, the top equation, I need to have PCl5 on the product side. In addition to that, I need to have 2 moles of PCl5, and in equation number 1, the coefficient is 1 mole of PCl5. So I'm going to take chemical equation number 1 and flip it. Not only will I flip it, but I will also double it. How can I do that? Because chemical reactions, in theory, are reversible. So I'm going to take a chemical equation number 1, I'm going to put a star by it, saying that that's a slightly different reaction as number 1, and I'm going to write it in the exact reverse way, in which PCl3, we lost it, there we are, PCl3 plus Cl2 reacts to make PCl3, and that is the exact flip of equation number 1. In addition to that, I'm going to double it, because in my target equation at the top I need 2 moles of PCl5 that should be A5. And in equation number 1 that I've changed, I only have 1 mole of PCl5. So I'm going to take a chemical equation number 1 and double it. So I'll have 2 moles of PCl3, 2 moles of Cl2, and finally 2 moles of PCl5. Now, what would happen to the amount of energy if I took equation number 1 and if I doubled it and I flipped it? Well, the delta H value was 87.9 beforehand in the first equation, but I doubled it. And that's now going to be 175.8 kilojoules. But I also flipped the reaction around. I made the products reactants and the reactants products. Before, the delta H was positive 87.9. Now the delta H value is going to be negative 175.8. How come? Because I had to double it and flip it. And that's going to be a 5. That's a bad 5. I will now take equation number 2 and equation number 1, and I'm going to add those two equations up to see if I get my equation, my target equation. Well, I look and I see that I have 2 P's on the reactant side in equation number 2. That's exactly what I wanted. So the 2 P's don't move anywhere. 2 P's plus, if I look very carefully, I have in equation number 2, 3 moles of chlorine plus an additional 2 moles of chlorine. So here's our 3 moles of chlorine, here's our 2 moles of chlorine. 3 moles of chlorine plus 2 moles of chlorine will give me 5 moles of chlorine. And I'm going to end up making 2 moles of PCl5 at the end. So, what happened to the 2 PCl3s? Well, the 2 PCl3s in equation number 2 and the 2 PCl3s in the equation number 1 that we changed slightly, these will cross off. These are present on both the product side and the reactant side in equal amounts. What we will now do is take these 2 equations, take the enthalpy or the energy in equation number 2, which was negative 574 kilojoules per mole, and equation number 1 that we flipped, which was negative 175.8 kilojoules. We're going to add those 2 values together, and we'll get a value of we will now get a value of negative 749.8 kilojoules per mole. So we now know if we were to perform this chemical reaction here, in which 2 moles of phosphorus and 5 moles of chlorine were to react to make 2 moles of PCl5, we would get 749.8 kilojoules of energy released from that reaction.